Another important aspect of subatomic particles is the fact that every subatomic particle has its partner, or an antiparticle. And that was due to the works of a man called Paul Dirac. Paul Dirac. Okay? Paul Dirac was a physicist who studied at, I think it was Cambridge University. Brilliant mathematician. He was very shy. But it was his work that basically he was doing some sort of a research into behavior of electrons or something, and from his works he found out that the electron, basically he was doing an equation and he found that the electron should have a partner, right, of the same mass, of the same spin, but of exactly the opposite charge, and that of course is the positron. The positron, or the positive electron. And essentially what they found was that in order to conserve certain laws, laws of lepton numbers for example, every particle, every subatomic particle has its own particle has an antiparticle. Yeah? Antiparticle. And antiparticles are of the same mass, same spin, but of opposite charge. And also of opposite lepton, or baryon number. Lepton number is very similar to a baryon number in the sense that a baryon number is basically baryon numbers and lepton numbers. What they are is kind of like binary. So if we have a neutron, is a neutron a baryon? Then its baryon number will be 1. But if we take an electron, is an electron a baryon? It's not, so we'll have a baryon number of 0. Get it? And if we look at it the other way, is a neutron a lepton? No, so it has a lepton number of 0. And if we think about the electron, is an electron a lepton? Yes, so it has a lepton number of 1. So that's essentially what it is. But if we have antiparticles, what you then end up with is them having different charges. So if we have an electron, its lepton number is 1. However, if we look at a positron, its lepton number is -1 because of the fact that it's an antiparticle. So that's something you might want to keep in mind. Okay? There's some things you might want to consider with antiparticles. First of all, the way you represent them. So if we have, for example, protons, neutrons, well, so let's have an electron here. Let's have an electron neutrino even. Okay? We have +1 charges. We have 0 charge here, -1 charge, and 0 charge here. We have baryon numbers of 1, 1, 0, 0, and then lepton numbers of 0, 1, 0, 0, 0, 1, 1, right? This is the baryon number, lepton number, and charge, right? Now, if I quickly move out the way here, let's actually zoom in again, sorry. If we look at the antiparticles, so if we look at the antiproton, and the way you represent it is with a bar over the P, you'll find that the charge will be -1, opposite charge. The baryon number will be -1. The lepton number will still be 0 because it's not a lepton. If you look at the neutron, its charge will be 0 because you can't get opposite of 0. Its baryon number will be -1, and its lepton number will stay 0 because it's not a lepton. For the positron, electron, for electrons you can just put a plus there, you don't need to put a bar. Its charge will be +1, its baryon number will be 0, and its lepton number will be +1. Sorry, my bad. -1 because it's the antiparticle. And the electron neutrino, the positive electron neutrino, represented with the bar, will have a charge of 0, will have a baryon number of 0, and will have a lepton number of -1. That's a good way to represent the differences between them, and it's a good way to visualize the differences between particles and their antiparticle partners. A concept that I'd like to introduce now is mass equivalence, mass energy equivalence. And the reason I want to introduce this now is because antiparticles and their counterparticles can react, and we'll get onto that. So quickly, we're going to talk about mass energy equivalence. Okay? Energy equivalence. You probably know an equation that defines what mass and energy, how mass and energy are linked. So pause the video and have a quick think about what this relationship might be and what the equation is that governs it. Alright? The equation, the most famous of them all, E is equal to mc squared. Einstein's equation. And essentially what this states is that energy is equal to the mass times by the speed of light squared. Okay? And this is an important idea that we might use when we're trying to deal with antimatter and pair production, annihilation, etc., etc. Right. If you have a beam of energy, okay? Let's say it's in the form of an electromagnetic wave, okay? You have energy. And of course, in an electromagnetic wave, the energy is represented by HF, right? If that energy is large enough, you can create mass, okay? Now, let me quickly point out something. If you look at this standard model over here, you'll find that energies are quoted in electron volts. Right? They're quoted in electron volts. And the conversion between energy in joules to electron volts is, you divide energy by the charge of an electron, and that gives you energy in electron volts. But the interesting thing is, this is also the mass of the particles. This is a way of representing the particle's mass because of the mass energy equivalence shown by Einstein's equation. Okay? So, wait, back to, I rubbed it off, my bad. E equals mc squared, and you have an electromagnetic wave with energy equal to hf, right? This energy, if it's large enough to create for example, if it's equivalent to one of the energies or masses shown here, you can actually create particles. However, there's one drawback. For example, let's say the energy is equal to 2 mega electron volts, okay? Let's say E is equal to 2.4 mega electron volts. And that's the same energy that's required for an up quark. You might think that we could then convert this. Oh, by the way, I have to mention, you can then convert electromagnetic waves into matter by using Einstein's equation. But this wouldn't work. So you can't take an EM wave and create one particle. You can't create an up quark, for example. And the reason why you can't do that is because you have to produce the antiparticle as well. So wherever you produce an up quark, you have to produce an anti-up quark. And this is called pair production. Pair production. And this is in order to conserve fundamental laws. You have to conserve laws like conserve charge. You have to conserve charge. You have to conserve baryon number. Baryon number. If we look at the equation, a virtual equation, let's say EM wave, right, goes to make just an up quark. The up quark will have a baryon number of 1, and it will have a charge of 1. We'll have a charge of plus 2/3, right? That's not conserving stuff. We need to, on this side we don't have any baryons. On the left hand side we don't have any baryons, but on the right side we have 1 baryon. We need to conserve that, and as a result we need the anti up quark, which has minus 2/3. And of course we have charge again on this side, which we don't have on the left side, and we need to conserve that as well. Conservation of charge, conservation of baryon numbers, those are all very important in why pair production occurs. Okay? So in essence, in order to create a particle, so let's say we wanted to create the let me clear this quickly. We wanted to create the up quark. If we wanted to create the up quark, we wouldn't, the energy of the energy of this EM wave would have to be equal to 2 times 2.4 mega electron volts in order to create the up quark and its antiparticle, the anti-up quark, right? And that's what pair production is. We discussed why it needs to be in play in order to conserve those different laws, and the energy, the mass of those particles can be worked out using E equals mc squared. So if E is equal to 2 times 2.4 volts, you can then work out what the mass is, and voila, you have your 2 particles. Okay? Right. Very similar to pair production is something called annihilation. Okay? Now, what annihilation is if we have an up quark and we have a anti-up quark. By the way, an anti-up quark is not a down quark. That's something you have to make sure you understand. Let's say they collide with each other, okay? They collide with each other at this point over here. Those 2 particles will have different velocities. Let's assume that they have very similar velocities. We know that you can use velocities and the mass of the particle to work out its kinetic energy, and that's given by half mv squared, right? And of course it'll be 2 times, assuming that they've got the same kinetic energy. When they collide, you'll have 2 times, you'll have the kinetic energies. They'll be it'll kind of be released, right? It's in essence what you'll get an annihilation of the 2 particles. The up quark and the anti-up quark will annihilate each other, and they'll produce EM waves, or electromagnetic waves. The energy of the electromagnetic waves will be equal to, each of them will have half of the mass of the particles. Sorry, 1 second. Each of them will have they'll have mass. Oh, sorry, 1 second. Let me quickly erase this. Each of the waves will have the mass of the up quark times by c squared, and in total you'll have 2 times that, because you have 2 particles. Notice that the 2 photons of energy are moving at right angles to each other. That's because you're conserving a law known as the conservation of momentum law. Conservation of momentum. if you're assuming a head-on collision between the up quark and the down quark, you have momentum in the you'll have zero momentum in the x-plane, and as a result, if you have particles that are moving then with components in the x-plane, you won't have conservation of those those two different conservation momentum in the x-plane. So in essence, you'll then have the movement of the particles in the y-plane opposite to each other, and because they're moving opposite to each other, they'll then cancel each other out, and you'll have a conservation of momentum again in that plane as well. So that's why they move in that particular direction. And in essence, that's what positron pair production annihilation is. It's the collision of a particle and its antiparticle that results in the emission of an electromagnetic wave. And of course, based on the energy, you can then classify it whether it's a gamma ray, or if it's an X-ray, or whatever it is based on the energy. And of course, that's linked by the E is equal to HF law, and you can work out what it is from that. That should conclude all that we need to talk about the subatomic particles. I'm just looking to see if there's anything else I need to mention. No, I think that's about it. So thanks for watching these series of videos, and I'll see you in the other physics lectures at some other point in the future. Catch you later.